thanks for coming to this talk on the robust Stackelberg equilibrium. So the Stackelberg game is a simple model that has many common applications, such as the security games, contract design, and even the poker games. So in this talk, we will focus on the normal form Stackelberg games, where the leader and follower has utility matrix UL and UF, and we use MN to denote the number of leader and follower actions. So the game has two stages. In the first stage, the leader takes randomized strategy X from some simplex, and then the follower would observe the leader's strategy X and subsequently take action J among his N actions. Finally, the leader and follower would receive utility UL and UF based on their strategy X and the follower's action J. Then a natural question to ask is how to design the optimal leader strategy. So the typical way is to assume that the follower is best responding, where here we can use the notation BRX to denote the set of best response set. And then it gives us the common notion of strong Stackelberg equilibrium, which is basically to find the optimal leader strategy given that the follower is best responding. And here it also assumes that almost without loss of generality that the follower is best with tie breaking in favor of the leader. So let me give you a concrete example on computing the strong Stackelberg equilibrium. Let's consider a simple example where the leader and follower has two actions. So in this utility matrix, in the first cell, the first entry stands for the leader's utility under I1, J1, and the second entry stands for the follower utility under I1, J1. Okay, so apparently in this utility matrix, the leader wants to have this cell of I1, J1 where he can get utility 100. So basically solving the strong Stackelberg equilibrium is equivalent in this example to solve a strategy X that has maximum measure on I1 and that the follower is best responding with J1. So it turns out that this action is basically for the leader to uniformly randomly play his action I1, J1. So this gives the strong Stackelberg equilibrium in this example. However, there's some practical concern on SSE. The first is that the follower might be bounded rational. And moreover, there might be uncertainty on the follower's utility and also uncertainty on the leader's mixed strategy. So if we go back to the previous example, all these concerns basically introduce some formats of noise to the utility matrix. And under this perturbed utility matrix, the follower might respond to the leader's strategy with J2. And this would let the leader end up with zero utility. And this is a bad situation we want to avoid in practice. So this paper is trying to design a robust variant of Stackelberg equilibrium that unifies previous concerns. Okay, to introduce our robust solution concept, let's first recall this definition of best response set. We use the notion called delta best response set, where for any delta greater than 0, this delta best response set contains all actions that are within utility gap delta to the optimal response. And then we introduce this notion called delta robust Stackelberg equilibrium, which is to solve the optimal leader strategy given that the follower is choosing the action that is the worst among his delta best response to the leader, which is essentially the so-called pessimistic tie-breaking practice. So this RSE notion is a general purpose robust solution concept that makes no assumption on the cause of suboptimal responses. So let me give you a concrete example, and we use the previous instance again. Basically here, it is trying to solve the optimal leader strategy that has maximum measure on I1, and the delta best response set of this X contains only J1. Because whenever this best response set contains J2, the follower would want to switch to J2 due to the pessimistic tie-breaking. And it turns out that we can compute the X star here, which is to take I1 with probability slightly less than 1/2, and I2 probability slightly more than 1/2. And we also want to remark that under this definition, the delta RSE exists in any game for any delta greater than 0. And this is actually due to a careful definition of delta best response set. That is, if we switch from this greater sign to greater equal sign in the definition, then this delta RSE may not exist. Okay, so in the rest of this talk, let me introduce some of the more property of RSE as well as its computability and learnability. So the first property about RSE is that we want to study how this delta affects delta RSE utility. So the first property is that this utility is non-increasing in delta and also upper and lower bounded by the utility of SSE and the utility of the minimax utility, where the follower is always choosing the worst response among his n actions to the leader. And we can illustrate this result in this way. Moreover, we've shown that there exists some constant delta, the big delta, such that whenever this small delta is less than big delta, the RSE utility is lower bounded by SSE minus some linear factors with respect to the small delta. And we call this delta the inducibility gap constant. And we can also show that this function of utility function of RSE is Lipschitz continuous within this interval between 0 and delta minus L. Interestingly, there is an economic interpretation of this constant for inducibility gap. That is, if we define the margin of an action J given X as the minimum utility gap between J and any other J prime, then the inducibility gap is basically the minimax margin of a game. And this intuitively means that the margin would relate to how easy it is to induce some action. And therefore, we give it the name inducibility gap. So notice that a game would always have this big delta greater than 0 as long as there is no action that cannot be induced. And we also remark that this continuity in the region where small delta is less than big delta, it enables better computational and statistical results. And we will have to refer to the audience to check out our paper for more details. Now let's consider the computability of RSE. The first is a negative result. That is NP hard to compute in 1/2n optimal delta RSE. And this is due to a reduction from the exact set cover problem. And this is a sharp contrast to the efficient algorithm to compute the exact SSE due to Cognizant Sandholm 2006. That said, we are able to show that there is a QP-test algorithm to compute the delta RSE. And let me give you an overview of this algorithm. So in the first step, we want to partition this simplex into K region with delta radius. Specifically, for each region, and satisfy the following condition. That is, for any point within this region, the leader's utility gap between this point and the a point called centroid is less than delta. So then the question is, what is the smallest k here? So due to the approximation lemma by Aslov 94, we actually only need to have this k on the scale of m to the log 2n divided by epsilon squared. And in fact, this similar technique is also used in approximating Nash equilibrium in Lipton et al. 2003. So now that we have those k regions, we can basically formulate the optimization program as to solve the best strategy in each region. But this optimization program is still hard to solve. Therefore, we consider a surrogate to this optimization objective. That is, we replace the x optimization variable x in the objective by the centroid of each partition block. And now the objective only depends on the variables through J. We claim that any optimal solution to the surrogate is an epsilon optimal solution to the original problem. This is due to the previous requirement, that is, any points within this region has utility difference less than epsilon to the centroid. Therefore, it only remains to solve this surrogate objective. So a naive approach is to partition this set Sk by the possible set of delta best response set. Here, for example, one region corresponds to best response set of 1 and 2, the other is 2 and 3. And then basically we can determine whichever best response set that gives the maximal leader utility. But this would take at most 2 to the n because there are that many delta best response set in a problem. So, but we can also optimize this time by instead partitioning this Sk by J star, which is the pessimistic the followers response after pessimistic tiebreaking. So now there's only n possible choices. So actually this trick can help us to achieve a speed up to n log n time using a carefully designed binary search procedure. And therefore, the final time complexity is k times O to the n log n. Next, let's consider the learnability of RSE. So we consider a setting where a learner is able to actively query a noisy sample of an entry in leader and followers utility matrix. And then we show that in a sample complexity mn divided by epsilon square, with high probability, one can learn an approximated delta RSE with leader's utility lower bounded by the RSE delta plus 4e RSE utility. So the challenge in this theorem proof is that whenever there's uncertainty about the follower utility, the best response set between the true under the true follower utility are different from the best response set, the delta best response set of the perturbed utility matrix. So how to bridge this gap? And the idea is that we can relate this delta plus 2e RSE in the perturb utility because we can show that the delta best response set under the utility matrix UF must be a subset of the delta plus 2e best response set under the perturb utility. And we want to remark that this bound is almost tight, and we have a proof with lower bound construction for different epsilon. And moreover, this has an implication for learning strong Stackelberg equilibrium. That is, we have this Mn divided by epsilon squared sample complexity of learning SSE for any epsilon less than big delta. And this actually substantially improves the statistical and complexity computational result for none of previous work for those non-degenerated instances. So as a conclusion, one takeaway is that this new solution concept of RSE gives a optimal design of robust leader strategy in practice. And this RSE enjoys reasonably good computational and sample complexity result in a large class of non-degenerated game. So for future directions, we want to design p-test algorithm for RSE or prove that it might not exist. And we also want to extend this RSE definition as well as its analysis to the more general principal agent games, such as contract design and information design problems.